So in this problem, we're going to look at an optimization problem where we use calculus to minimize an area. So this example says a rectangular page needs to contain 36 square inches of print. So that's the written word, written content. So 36 square inches of print. The page margins must be 1.5 inches. Find the page dimensions that meet those requirements, but they use as little paper as possible. So if you're trying to minimize the amount of paper that you're using, you have a sheet of paper. Then you're really trying to minimize area. And there's going to be two different ways that you can set this problem up, and we really want to look at both of them. So we have a piece of paper, we have print area. So the print area is going to be on the interior of the sheet of paper. So you have a rectangle within a rectangle, and we're told that we need to have 1.5 inch margins all the way around. So each of these dimensions are going to be 1 and 1/2, and that will include this dimension here. So I'm going to set this up two different ways, and then what you'll see is that you need to make the decision for yourself which of the two ways you use to set this up. So margins are still going to be the 1.5 inch margins all the way around. I'm not going to label the numbers in again. Just those are 1.5 inch margins where the arrows are. So one way to do this is you can identify the page height and width on the interior where the print area is. So this part in here is the print area. This is the part that needs to be 36 inches squared. So if I make the H and the W correspond directly to the print area, then what I get is that height times width equals 36. But using as little paper as possible, I'm trying to minimize the area of the entire sheet of paper. So this function here, or this model, doesn't describe the area of the paper itself that's being used. So what I would need to notice is that the area of the entire sheet of paper, I would need to get that by taking the interior width and then adding, there's 1.5 extra inches to a side, so the outer width is actually going to be the interior width plus 3. And the height of the outer sheet of paper would actually be the interior height plus the 3 inches you get from 1.5 inch margin here plus 1.5 inch margin here. So you actually get height plus 3. So the area of the entire sheet of paper is going to be the width of the paper, which is the interior width plus 3, times the height of the paper, which is the interior width plus 3. So there's one possible setup for an area function. And then remember, we need to find area as a function of a single variable. This is area as a function of interior width and interior height. So we would need to replace either the W or the H in terms of the other variable, and you would do that using the print area here. Height times width equals 36. So for example, this would tell us that height is equal to, divide both sides by W, 36 over W, and then we could replace the height right here in the area model with 36 over W, and we would have area as a function of a single variable. So that's one possibility. That's possibility number one. Possibility number two would be to let width describe the outer width of the sheet of paper, and to let H or height describe the outer height of the sheet of paper. But then the interior, you would have to, instead of adding 3 like we did here, you would have to subtract the 3 inches of horizontal margin. And then right here, to get the interior height, you would have to subtract, again, the 3 inches of horizontal margin. So we would need, for the print area, we would actually get width minus 3 times height minus 3. The interior area needs to be 36 square inches, and then the area of the paper itself would actually be width times height, or height times width, depending on how you want to do it. And then to write the area function as a function of a single variable, we would need to solve this expression, or this equation here, for either height or width. So for example, if we solved it for height, we would divide both sides by w minus 3. So we'd wind up with a height minus 3 equaling 36 over w minus 3. And then we'd have to add that 3 to both sides, and then we would substitute this in for height. So you'd get area equals, and you'd have 36 over w minus 3 plus 3 all times the width. Whereas here, if you solve for height, you get h equals 36 over w. So your model winds up looking like this: width plus 3 times 36 over w plus 3. And so you're either going to be working with this model or this model, and you really need to decide for yourself which of the two models you think is going to be easier to work with. In general, I like working with this model because I like using this simple substitution here. So I'm going to erase this example. Either setup is correct. The problem, the downside to using height and width to represent the interior dimensions, is we want the entire page dimensions. So whatever result we get for width and height, we wind up having to add 3 to each of those dimensions to get the actual page dimensions. Hopefully that makes sense. So using example 1, I let height and width represent the interior print area of the page. So height times width has to be constrained by 36 square inches. I can solve that for height by dividing by width on both sides. My area function for the page itself, which is what we're actually trying to minimize, right, uses little paper, so minimize it. It's going to be width plus 3 times height plus 3, the area of the outer rectangle. Now I want to establish some sort of feasible domain for this. And in this case, it's a little bit more difficult than it was in the first two examples. What I want to recognize is that the width, here I have area as a function of just width. Well, the width can't be negative, so I know the width has to be greater than or equal to 0, but if I try plugging in width equal to 0 right here, I get a division by 0. So 0 isn't in the domain of my area function. So I'm going to say, hey, width is an element. I'm going to work with an open interval, which means I can't directly apply, unfortunately, the extreme value theorem. So I can say, well, I know width has to be greater than 0, and there's really nothing to put an upper bound on what the width can be. So I'm going to say, hey, the width is going to be on the open interval from 0 to infinity. So we want to think about this a little bit. So if I'm thinking about the graph, what's going on with the graph? I have an area function here, and it's a function of width. And I know that I don't need to worry about anything over here because these correspond to negative widths. And I don't need to worry about anything down here, which would correspond to negative areas. So I'm only going to be concerned with the part of the graph of the area function that lives in quadrant 1, where both width and area give me positive real numbers. So that's the first thing to realize. Now I want to recognize that when w, or width, equals 0, I get a vertical asymptote. So actually the area axis, which corresponds to w equals 0, is a vertical asymptote. I want to notice that. And then if I look at this differently for just a second, let's grab our area function and say, hey, I've got the w plus 3, and this is a 36 over w plus 3. Well, if we get a common denominator for this thing, you'd actually get w plus 3 times, we would get 36, and we would multiply this by w over w, so we'd have 36 plus 3w over w, which is just a rational function. It's the polynomial w plus 3 times 36 plus 3w in the numerator over w. So we could actually think about what happens to the area function as we let the width go to infinity. What is the limit as the width goes to infinity of our area function? And that's going to just equal the limit as w goes to infinity. And this is something that you would have done in pre-calculus. You would have said, hey, if I have a rational function in pre-calculus, you identified that the largest degree term in the numerator and the largest degree term in the denominator were the only things you needed to worry about to get the limit as w went to plus or minus infinity. So the largest degree term in the numerator is going to be this 3w right here times the w here, which is just a 3w squared. And then the w's, you're going to get some cancellation, so you're going to get the limit as w goes to infinity of 3 times w when you simplify that. And when w goes to infinity, 3 times w goes to infinity. So I know the area function goes to infinity as w goes to infinity. So let's think about what has to happen. When I look at this rational function here, what I want to notice is that w plus 3 is positive for all w on the interval from 0 to infinity. W is positive on this interval. So this is a positive number. 36 times 3 plus w is a positive number, and w is a positive number. So the area is always positive. The area is always positive when w is greater than 0. So I know I have a vertical asymptote at w equals 0. So what this tells me is that my area function has to come down my vertical asymptote. It's going to have to reach some low point, and then as w goes to infinity, the area has to go back to infinity. So my function is going to go back like this again. So what I can see is that's going to force a low point on the function. So when I find the critical number, whatever it is, it's going to correspond to a minimum in quadrant 1. In fact, if we take the second derivative of a, we should find that the graph is in quadrant 1 concave up, which means if we find a critical value, it's going to be a minimum value. So that's a key to recognize from the graph, is to notice that on the interval from 0 to infinity, when I find that critical number, I'm expecting it to correspond to a minimum. And I was able to identify that basically using pre-calculus skill set. So here's the area function. We're going to need to find the critical numbers for this area function. So we're going to have to take its derivative. So it's probably going to make sense to multiply these two guys out. So w times 36w is just 36. W times 3 is 3w, plus 3 times 36 over w is just 3 times 36 over w. I'm not going to worry about multiplying those out. Plus, and I get 3 times 3 is 9. And then what I want to recognize is if I want to take the derivative, it might be convenient to put the w into the numerator position, which would mean write the w in the numerator position with an exponent of -1. That might help me to think about things. Now let's go through and take the derivative. The derivative of 36 is 0. The derivative of 3w is just 3. The derivative of 3 times 36w to the negative first, that negative is going to come down. And it's going to be -1 times 3 times 36, and it's going to be w to the -2, and the derivative of 9 is just 0. So here's my derivative. And in fact, if I wanted to, if I had some interest, I could take the second derivative. So I'd get the derivative of 3 is 0. The derivative of the next term, the -2, is going to come down and cancel the minus sign right there. So I'm going to get +2 times 3 times 36 times w to the -3rd power, which is the same as putting the w in the denominator position to the +3rd power. And what I can notice here is that as long as w is positive, which it is on the open interval from 0 to infinity, a double prime is actually greater than 0. It's a positive number for any w greater than 0. And because the second derivative for any w greater than 0 is positive, I know my graph is concave up in quadrant 1, where the values for W are positive. So I know from using my second derivative test that I have a concave up graph in quadrant 1. So if I find a critical number C, it is going to correspond to a minimum. And there's my justification that I'll be using, if I find the critical number, as little paper as possible. So the critical number, remember that we find that by focusing on the derivative. So let's focus on our derivative for a minute. So we have A equals, and it's 3 minus 3 times 36 times W to the negative first. If I want to have a positive exponent, I would just move that W down and make it to the positive first instead. But W to the positive first is just W. So remember, we get critical numbers when either A is undefined or when, sorry, this is A prime. We get critical numbers when A prime is either undefined or equal to 0. So here I notice that A prime is undefined when W is equal to 0. But I don't need to worry about that because W equal to 0 isn't part of the feasible domain that we've established for our function. So I don't have to worry about that. I just need to worry about when is my derivative equal to 0. And that's going to give me a critical number that corresponds to a low point on the graph of the area function in quadrant 1. So set the derivative equal to 0. And now you'll see why I didn't bother multiplying these out, because now I can add 3 times 36 over W to both sides. 3 times 36 over W is going to equal 3. And notice if we divide both sides by 3, those 3's will cancel, giving us a 1. And I lost my squaring right there. That should be, this was W, 3 minus 3 times 36, W to the negative 2. So when I move the W down, it should be squared. Right, I lost the squaring right there. Probably because I wrote it sloppily. We took the derivative, so we had to subtract 1 from negative 1 to get the negative 2. When we bring it over here, it's going to be to the negative second power, but I can put this down into the denominator position, making the exponent positive. So if I do that, I add this term to both sides, and then I got 3 times 36 over W squared equaling 3. But I can divide out the 3 on both sides because it shows up on both sides, and then multiply both sides by W squared. I get 36 equals W squared. So you can see that I never really needed to multiply that 3 times 36 out. And now you would take the square root of both sides, and you'll get plus or minus the square root of 36 is 6, equaling the square root of W squared is W. But negative 6 isn't in our feasible domain, so we know that we don't have to worry about the negative 6. So a width of 6 inches on the interior should correspond to a maximum area for our page. I'm going to get my height that goes with that. We know that height times width needs to equal 36 from right here. So if the width is 6, we'll see that height also needs to be 6, so we want, it looks like we're after a square in this particular case, and this is probably driven mainly because the margins are evenly spaced all around. We'd come up with something different if we had the side-to-side margins different from the up-down margins here. And then what I am after is the page dimensions. And what we needed to remember, because of the technique that we used, whatever value we got for W and H, we had to add 3 to that in the end to get the dimensions of the page. So the page dimensions are going to be 6 plus 3 inches is 9 inches by height plus 3 inches. 6 plus 3 is going to be 9 inches by 9 inches. Again, this turning out to be a square is probably driven primarily, I need to think about it a little bit, but probably driven primarily by the fact that we chose these page margins to be the same all the way around. So we'd have to think about, well, what would happen if we let the page margins differ on the sides than on those horizontal margins on the top and bottom.